Hi there, I know I'm a tad bit late on this video. I've done several videos about example problems for the disk method, the shell method, and the washer method of finding volumes of revolved solids that have some sort of axis of symmetry. But I wanted to go through and kind of derive these equations with you so that you have a better understanding on how to use them. So let's go ahead and start out with our basic disk method, which is usually the first one we learn. So in this case, you'll see this arrow is representing a rotation about the y-axis. The problem will say revolve about the y-axis, or something like that to indicate when we do something like this. So the first thing to do is to figure out what is our small segment of area that we're going to actually revolve. Well, first let's even just visualize this. So if I revolve from A to B here, if I revolve this around the y-axis, I would end up with some sort of a bowl that had, it would have a cylindrical external, and then it would have some sort of a paraboloid or spherical interior where this inner part of the curve would be rotated. And so we're interested in figuring out how we're going to use a disk to do this. And so, well, actually, this is going to be a washer method, oddly enough. So let's go ahead, because disk and washer, they're very, very similar. I guess we'll start with the washer. So you want some sort of, because we're rotating about the y-axis with a washer method, our small little infinitesimal is going to be dy. So the width of this is infinitesimally small, and we're calling it dy because it's a small bit in the y direction. And we're going to go ahead and revolve this little infinitesimal area into 3 dimensions. And of course, when you extrude area into the 3rd dimension, you end up with volume. So if we rotate this thing about the y-axis and we look at this washer that we've created, and this is why it's called the washer method. So we've created this washer. And you'll notice that even though we revolve this into 3 space, it still has a height of dy, right? Because this little strip that we revolved had well, I guess you could call it a height of dy. And then you'll notice with the washer method, there's 2 important other measurements. One is the interior radius. I'm going to go ahead and call that R1, big R1. It doesn't really matter what you call it. And then we go ahead and we have an exterior radius. I'm going to call that R2. And now we're going to try to figure out, see, the beautiful thing about calculus is if you figure out what happens at your most minimal level, then you can just integrate that whole idea across the whole parameter that we're trying to find the volume for. So what we need to do here is we need to figure out some of the dimensions for this specific example. So we have to apply it to this graph. So you'll notice here that if we were looking at the radius 1 of this strip that we revolved, you'll notice that the radius 1, when we drop it down, would actually be an x value. So in other words, whatever x you were plugging into f of x is what your inner radius would be. Because if I plug in x here, then my graph that I'm following will be up here. And so our inner radius, or radius 1 in this case, is just going to be whatever x value your function is using at that particular point in time, whatever the input x value is. And then we're going to go ahead and figure out, well, what is R2? Well, you'll notice that, oh, and by the way, I'd like to point out that this is going to work for every possible strip. So in other words, if I picked my strip to be here or here, you would notice that the inner radius is still, in fact, the x value for this graph f of x. And likewise up here would still be the x value. So it works for our entire interval that we're integrating across. And you'll notice that the outer radius for every single one of these different strips that we're revolving into washers is actually the distance from A to B. So in other words, in this case, what we've got here is we've got R2 for every point, for every different strip, is going to be A minus B. Or I'm sorry, B minus A. And, let's go ahead and give them numbers to make it a little easier. Let's say X was 0, and let's say B was 5. So then 5 minus 0 would give us an outer radius of 5. And so now to set up the integral, so we figured out what our radiuses are and what our height is. Now we need to figure out what dV is. And dV stands for an infinitesimal amount of volume, which is shown in this washer. It's the volume that is encapsulated by this washer. And so my first step is I look and I say, if I can find the area, the surface area, and then times it by the height, dy, that will give me my small chunk of volume. But it's important to realize that if we take the area of the outer, so in other words, if we take the area of this outer R2, so in other words, pi R2 squared would give us this whole area, including this little interior chunk that's been cut out. And then we subtracted the inner radius's area, so that would be pi R1 squared. Then we would actually, so we started out by saying, well, let's find all of this area on the surface. And then when we subtracted the area of the smaller circle, we cleaned out this inner part, and we found an accurate representation of our surface area that's actually represented. Well, now we just need to multiply that surface area by the height, which is, of course, dy. It's still dy, the height is. And so we can simplify this a little bit further. We could say that dV equals, well, we could pull pi out of everything, right? We could pull pi out of both terms. R2 squared minus R1 squared. And, of course, we found that R1 is x, so we could plug that in. And we found that R2 is 5 for this specific example. And this is why I like drawing these things out, is because there's always going to be a very specific thing that we're trying to revolve. And so it's important to look at what you're working with and kind of conceptualize what we're doing. And that's all going to be multiplied by the infinitesimal with dy. So 5 squared is 25, so we've got pi 25 minus x squared dy equals dv. Well, here's kind of an important thing to remember, is that we're not in multivariable calculus yet. So if we're integrating with respect to dy, we need everything in terms of y that's not a constant. So we know what x is in terms of y, because f of x, let's say f of x equals x squared. Well, what that also means is that, for example, y equals x squared, we could take the square root of both sides and find that x equals the square root of y. And so then we could go ahead and do the substitution. If x equals the square root of y, the square root of y squared is just y. So we do that substitution. And here's where the magic happens. We've figured out what this infinitesimal chunk of volume is and how to map it as we integrate on the y-axis from here to there. So the next step is to take the integral of both sides. Well, the integral of 1, because there's a little invisible 1 in here, with respect to dv, is just v. Because the integral of 1 dx would be just x, so the integral of 1 dv would just be v. So that's the volume that we're looking for. And now we're integrating from a to b this function pi times 25 minus y with respect to y. And there's one last thing we need to figure out, because we know our a and our b and our x coordinate, but one thing that we don't know, because remember we're integrating these washers up up this curve. And so we're integrating with respect to y. And so we need to know our beginning, so we need to know our y, our boundary for our y, our lower boundary, and we also need to know our upper boundary. Now the lower boundary is obvious for x squared, it's just 0 because x squared passes through the origin. But for y we could solve because we know that x equals 5, so if we plug in 5 to our function, it will give us this upper boundary. So let's plug in 5. So y equals x squared. Well, x is 5. Y equals 5 squared. So therefore y equals 25, which means that our upper bound is 25. And now we know that our lower bound is 0, and our upper bound is 25. And at this point, the integration isn't all too bad. You've got a constant value here and a variable value, but it's just going to be a reverse power rule that you're going to use to integrate this. So this is how we might set up an integral that's using washers. Next video I'll talk about disks and shells, and hopefully this is helping conceptualize, because the equations are on your cheat sheet, but unless you know when the equations apply and how they apply, it's going to be really hard to use these equations in the right way. So personally, I prefer to derive the problems like this almost every time if I can find the time to do so. So I hope this was helpful, and I'll see you next video.